So I'm going to start the recording. So section 8.2 in the textbook, there's a lot of notation and theory and stuff like that that to me can be, well, it isn't necessary for you to really. We're only covering a certain part of section 8.2, and the part that you're going to be responsible for, if you understand this example I'm doing, I think you should be good. So let me give you a moment to copy down this example from section 8.2, and then we'll go over the solution. Oh, yes, Andre. A typo? Do I have a typo here? Michio. Well, all right. So what we want to do, we're in, Andre, the outcomes assessment questions are like actual problems, but you should do fine on them based on what I've taught you. You should do fine on them. All right, very good, very good. Thank you. All right, so we've talked about solving differential equations, okay, and but also in life we have systems of differential equations, and as a matter of fact, you learned, for instance, in MATLAB assignment the number 5, how you can take a second order differential equation and express it as a system of differential equations to produce like a direction field and so forth. But also there are plenty of applications where you need to solve several differential equations at the same time. And you actually saw that in, I believe it was MATLAB assignment number 4, where you had a predator-prey model, rabbits and foxes, and you had 2 differential equations to model the growth rate, one differential equation to model the growth rate for rabbits, another differential equation to model the growth rate for the predators, like the foxes. 2 differential equations. But in that example, in the MATLAB, in MATLAB assignment number 4, there, you solve that system of equations. You use like Euler's method to help you because they were nonlinear differential equations. Okay, and so what we're focusing here in section 8.2 is what's called a linear. It's a linear system of differential equations. So you have 2 differential equations below, and you notice before the x and the y you have constants. That's a 1 there. You have constants. This is just called a linear system of differential equations. And it turns out that we can solve linear systems of differential equations quite nicely. Now, what I'm showing you applies to our system of 2 differential equations, but the theory I'm going to teach you applies if you had a system of 3 linear, if you had a linear system of 3 differential equations or 4 differential equations. What I'm teaching you would apply. Okay. So, are there any questions before we move to the solution here? All right. So, okay, how do we solve this linear system of differential equations? Well, first, we really have to get some notation down. Okay, so I'm going to use what's called matrix notation to denote this system of differential equations. Okay, so what I'm going to do is I'm going to define a vector x. How many have seen vectors maybe in like a physics class or another class, a vector? Okay, Andrea has seen it, and Sure, and vectors can be used to represent like forces, and a vector has a direction and a magnitude. But we're just, because the book and the WebAssign problems are going to use matrix notation, I want to make sure you're comfortable with it. So what I'm going to do is I'm going to have a vector here, and this vector is a 2 by 1 vector. Okay, this vector here has 2 rows and 1 column. So the xy, I'm going to call my big vector x. And whenever you have a vector, to denote a vector, you have an arrow above the symbol. We usually make the vectors can be capital or non-capital, but we always have the arrow above. Now, the way the book will denote a vector in section 8.2 is it will have a bold-faced x. That stands for vector. And x and y are our components of this vector, but we have to remember that x is a function of t and y is a function of t by virtue of the fact that our differential equations are dx dt equals something and dy dt equals something. That implies that x is a function of t and y is a function of t. Now, what we want to do is we want to say, okay, well, what would the derivative of my vector x be? I would denote that as the derivative vector x prime of t, or dx vector dt, and that's just going to be the vector that has the derivatives of x and y. So if the matrix A then has these numbers in it, 2, 3, 2, and 1, and I'll come back to this, you'll notice that 2, 3, 2, and 1 are the same, they're the coefficients of x and y. Okay, you got a 1 there, the coefficients of x and y in our system. So that's how I come up that A equals 2, 3, 2, 1, that 2 by 2 matrix. This is a 2 by 2 matrix. It has 2 rows and 2 columns. So if I want to write my system of differential equations using matrix notation, it would be equal to the derivative vector x prime of t equals a of x of t, where I've denoted the x prime, the a, and the x as you see there. Okay, and incidentally, I might make a point here as well that you're multiplying this 2 by 2 matrix A by this 2 by 1 vector xy. Okay, let me try to make it, hold on. Try to make it a little better here. One moment. Okay, so you have this 2 by 2 matrix, 2 rows, 2 columns, multiplying by this 2 by 1 matrix, this vector. Vector has 2 rows and 2 columns. And since the column number of the first matrix matches the row number of the second matrix, then we can multiply these two matrices. And when you multiply 2 matrices, you multiply the row times a column. So for the first component here, you're going to have 2 times x plus 3 times y. And for the second component, you're going to take the second row and multiply it by that column. And that's going to get you 2 times x plus 1 times y. Okay. And let me close the bracket there. And so you have then that dx dt has to equal 2x plus 3y, and dy dt has to equal, because this is an equals here, right? Hold on, let me make that a little darker. This is an equals. Dy dt has to equal 2x plus 1y. So this is due to matrix multiplication. How many maybe have learned how to multiply matrices maybe in another class, or in high school, or how many have done that? If linear algebra, math 284 is a great course if you want to do that, right? But how many have seen that before, maybe in another class? All right, Max is familiar with it. He Hyung, AP Calc, okay, has seen it. Okay, so are there any questions about taking our our linear system of differential equations, and writing that system as in terms of matrix notation? Are we all right with that? All right, if we're good, may I go to the next page? Let you maybe give me a thumbs up if Andrea's ready. Very good. Okay, maybe give me I'll wait for a few more thumbs ups. Okay, good. Joseph's good. Excellent. So what we need to do, of course, and Christopher's good. Excellent. Excellent. What we need to do is to be able to solve this system of differential equations. We need to be able to solve it. So there is a theory. Well, the theory says we can solve a linear system of differential equations by finding what are called eigenvalues and eigenvectors of the matrix A. Okay, so this matrix A here, we have to find what are called eigenvalues and eigenvectors. So, and we'll talk about that. But what are eigenvalues and eigenvectors? Well, okay, so if you consider the matrix equation A times vector v1 equals a scalar, lambda here is a scalar, times vector v1. If you could find a vector of two numbers, remember A is 2 by 2 matrix, so the vectors we're dealing with are 2 by 1s. If there were a matrix v1, okay, such that A times v1 were equal to lambda 1, this should be lambda 1 times v1, then lambda 1 would be an eigenvalue, and v1 would be the eigenvector corresponding to that eigenvalue. Similarly, if the matrix A times some vector v2 were equal to lambda 2 times v2, here, then lambda 2 would be an eigenvalue, and the vector v2 that 2 by 1 vector of whatever numbers are in there would be an eigenvector corresponding to lambda 2. Now, in linear algebra, in Math 284, when we try to find eigenvalues and eigenvectors, we show theoretically how to do it. We actually, I mean, basically these two equations, these two what we call matrix equations here, turn out to be basically a system of equations. You can solve a system of equations, but we're not going to worry about that. We're going to let MATLAB help us find our eigenvalues and eigenvectors. And I actually have a program. If you look in Blackboard under MATLAB programs, there is a program. There's a section 8.2 topic there, a thing where you click on it, and then you can access the program. So, okay, it turns out that the solution, if we want to solve our linear system of equations, and a lot of times they suppress the t when they have a linear system of differential equations. They just write the system as x prime equals a times x. And you notice I keep the vector symbols on there, right? The notation's important. So the general solution is here, given here. So the solution x is equal to, so it's a general solution. General solutions, as you know, have constants in them. Okay, it's when you specify initial values that you can solve for the constants. You've seen that all throughout the course. This general solution, it turns out, is going to be equal to a linear combination of what are called eigenfunctions. Okay. The eigenfunction here is defined as e to the lambda 1 to the tth power times the eigenvector v1. And the second eigenfunction here is defined as e to the lambda 2t times the eigenvector v2. And we always keep in mind that vectors v1 and v2 have numbers in them. Okay, those don't have variables, they have numbers in them. Now, I think it would be valuable for you, I'll wait, of course, till you're done copying, but I think it would be valuable that you see a proof of why this is true. I think this would be of value to you. I mean, so what we're going to do on the next page is actually prove why we can have a solution of a linear system of differential equations given in this form. And incidentally, if you had a 3 by 3 matrix A, you would have, you know, C2 times e to the lambda 3t times an eigenvector v3. I mean, it just builds and builds depending on how large your matrix is. Okay. Are there any questions? Okay, well, just give me a thumbs up when you're ready to move to the next page. Okay, thank you, Max. In your notes now, be sure to use those vector symbols. Sometimes students are a little, you know, they get a little bit lazy and they don't want to put their vector symbol above there, but it is important for your notes. And you know, on the final exam, I like proper notation there too. And All right. All right. Shall we move to the next page, class? Okay. Thank you, Andrea. Okay. So let's prove why this is true. You know, I always think it's nice if you can understand why things are true when you do them, right? As in math as in life. So what we need to do is show that this solution is indeed a solution to our linear system of differential equations. And the way we do that is we say, okay, let's start off with this solution. Let's start off with this solution and let's take its derivative. Let's take its derivative. Well, the solution, the solution, each eigenfunction has the e, well, the first eigenfunction has e to the lambda 1 to the tth power, and the second eigenfunction has e to the lambda 2, I'm sorry, the first eigenfunction has e to the power lambda 1t, the second eigenfunction has e to the power lambda 2t. Now that is what that's our function of t. So those are the only functions of t that are like in our solution. So when I differentiate, okay, if I want to differentiate, for instance, well, I want to. I'm going to take the derivative, right? But if I differentiate this first term, if I'm going to differentiate this solution x, then I have to differentiate each term with respect to t. Well, the derivative of e to the power lambda 1t is just lambda 1 times e to the power lambda 1t. By the, let me get that, hold on. Let me get that off here. Very good. The derivative of e to the lambda 2t by the chain rule is just lambda 2, it's just lambda 2 times e to the lambda 2t. Everything else are constants, okay? Now, what happens next? What happens next? Well, what I can do is the e to the lambda t, I can rearrange my terms. Okay, I can rearrange my terms here. So when I rearrange my terms, my eigenvector, my eigenvector v1 stays where it is, but I'm going to bring the e to the lambda 1 to the tth power. That's a scalar function, right? I mean, well, it's a function of t, but it's a scalar function of t. I'm going to bring that over here. It's just like, you know, when you multiply terms together, you can rearrange the terms. Okay, and I do the same thing here for e to the lambda 2t. I just bring it in front of that lambda 2t. So then I end up getting this expression here. But you see, lambda 1 times V1 is equal to AV1 because lambda 1 is an eigenvalue and V1 is an eigenvector. So by definition, A times the eigenvector V1, that equals lambda 1 times V1. And similarly, lambda 2 times the eigenvector V2 would equal the matrix A times the eigenvector V2. And this is only true because lambda 1 is an eigenvalue and V1 is an eigenvector, and also lambda 2 is an eigenvalue, and V2 is its corresponding eigenvector. That's the only reason we can do this. But what we do now is I just rewrite it. I rewrite it here, the expression for our derivative vector. And then what I do is the matrix A, I can bring it out in front of these scalars. Okay, the matrix A can be brought out in front of scalars. Now, if this here were a matrix, then I couldn't do this. I couldn't bring the matrix A out in front of the terms. But since C1 e to the lambda 1t and C2 e to the lambda 2t, since those are just scalar functions of t, I can move my matrix A out in front. Okay. How many maybe have seen that kind of matrix rule? Have some basic matrix rules, maybe in past classes. Well, and so you're seeing it now. And now what I do is I factor out the matrix A from both of these terms here, okay, I have a matrix A in common between both terms. And so I can factor the matrix A out on the left. And so I end up getting that the derivative of my vector x is equal to A times this big vector here. But what is that vector? This vector here is just the x vector. So I end up getting that with this choice of a solution, or with this choice of what I think is a solution, it works out because with that choice, we end up getting that x prime, the derivative of x, is equal to the matrix A times the vector x. And therefore, this shows, should have an S here. This shows that that this is indeed a solution to that system of linear equations. And actually what I've shown you is something that we do in linear algebra, Math 284. And it's a great course if you ever need to take a, if you're considering some other 200 level courses. Multivariable is also good. I'm teaching that over the summer and in the fall. Okay, so are there any questions before we move on? Okay. Um, may I go to the next page? Maybe give me a thumbs up if you're ready, or when you're ready. Thank you, Paige. Thank you, Andrea. Okay, so now what we want to do, now that we're comfortable on what a solution to the linear system of differential equations is, now what we have to do is find our eigenvalues and eigenvectors. Okay, and there is a program that will do this for you. Okay, there's a program that will do this for you. So let me go ahead here and bring up that program. Okay, so one moment here. Let me go into the Blackboard. Okay, and you look under, let me just make sure it's showing up well here. One moment. Yeah, make that a little bigger. Yeah, look under MATLAB programs here. And click here to see MATLAB programs. Click there. And then there is there's section 8.2, the new program. And just click on that MATLAB program link, and it will bring up the program. Okay, so what I'd like to do now is go into the MATLAB. So let me now everybody's good here, hopefully. Go into MATLAB, right? Okay, and here is the program. And what we're doing, actually, the problem we're doing, it corresponds to example 1 from section 8.2. Okay. So what I do first of all is I have the command clear vars. That clears the variables. If there are any variables, I don't want any variables to possibly interfere with my program. And then this is how you type a matrix in. Okay, this is how you type a matrix in WebAssign. The first row is 2, 3. You separate that then from the second row, which has 2, 1, by a semicolon. And then you use the command right here to find the eigenvalues and eigenvectors. So for section 8.2, you will be able to use MATLAB to find all eigenvalues and eigenvectors. You do not need to find eigenvalues and eigenvectors by hand. You may use this MATLAB program. And incidentally, if we had a matrix, say, that were a 3 by 3 matrix, we would use the same code. It's just on that line 6 where you have the matrix A, you'd have to have a matrix that you'd have to enter a matrix with three rows. That's all. That's all. So are there any questions on that? Let me go ahead actually and copy the code and paste it on the command line. Paste it here. And we get our output very quickly. That's right, Zachary. You do not need to find eigenvalues and eigenvectors by hand. In the textbook, they show the theory and how to find eigenvectors and eigenvalues by hand. Oh, sorry. I see that. Hold on. I don't know how that happened. One moment. Thank you. One moment. Sorry, let me find it here. Here it is. Okay. Everybody can see the screen now. Yes, to your question, Zachary, good question. In the textbook, in section 8.2, they show in examples how to find eigenvalues and eigenvectors by hand. You do not need to find eigenvalues and eigenvectors by hand for section 8.2. You may use this MATLAB code to get your eigenvalues and eigenvectors. And you'll see there on the left, there's two things on the left there in the command line. Okay, two things here. Sorry, I just want to make this a little bigger. Did it go? Hold on. All right, so this here, the EVL stands for eigenvalues, and there are two of them, the -1 and the 4. You ignore the zeros. You ignore the zeros. -1 and 4 are your eigenvalues. Now for the -1, the eigenvector is under EVR, and you look vertically. You look vertically. So the eigenvector, the first eigenvector is -1, 1. Okay, on the left there, look under EVR. The first eigenvector is -1, 1. The second eigenvector is 3/2, 1. Those are your so now you found your eigenvalues and eigenvectors. Are there any questions on that before I go back to the example? Okay, let's go back to the example then. Let me see here, hold on. Okay, so using the MATLAB program, we've computed the eigenvalues and eigenvectors, as you see here. So now that we have that, the general solution to our linear system of differential equations is right here. It's right there. It's a general solution because we have C1 and C2. C1 and C2. Here's e to the lambda 1t. Here's e to the lambda 2t. Okay, and then here are the eigenvectors that we found. Okay, the eigenvectors v1 and the eigenvectors v2. So, this example we're doing, where we have dx dt equals that, the one differential equation, dx dt, and the other one is dy dt. So that models, like velocities with respect to the x and y direction, right? Right. So, I mean, this. I don't know if you've seen this kind of thing in physics, but we can model like trajectories and so forth based off of the system of differential equations. Now this answer here differs a little bit from the answer for example 1, but it should be fine. Okay, WebAssign should accept. So eigenvectors, the textbook for this example for this second eigenvector, instead of 3/2 and 1, okay, instead of 3/2 and 1, they have 3 and 2 as the components. Any multiple of an eigenvector is itself an eigenvector. So like if you wanted like nice simple eigenvectors, instead of 3/2 and 1, you could use 3 and 2. You just multiply that vector by 2. And incidentally, the first eigenvector, the textbook has it as 1 and -1. We have -1 and 1. Well, if you multiply that eigenvector by -1, you'll get what the textbook has. But it's okay. Okay, you don't have to get the same answer as the textbook has. All right. Are there any questions before we move on here? It just has to be a multiple. That's correct, Zachary. Just has to be a multiple. And now, you know, at this stage, we have a general solution. But remember, we were given initial conditions. We were given initial conditions on x and y. We were told that x of 0 was equal to 1. And we were told that y of 0 was equal to 4. So this trajectory, okay, would be start off at the point 1, 4 when time equals 0. At time equals 0. So it's a specific trajectory, so we have to solve for C1 and C2. And of course, we have two constants to solve for. We need two pieces of information, and we have them here. So now let's explore how we're going to solve for those two constants. All right. So if there are no questions, then I'll move on to the next page. Okay. So here's how we solve for C1 and C2. At time 0, the vector x of 0 is equal to 1, 4. Right? Well, we put t equals 0 in then for the t's. In our solution, we let t equal 0. And we end up then with what's called a vector equation. In other words, 1, 4, that vector will equal the sum of these two vectors. The first vector, negative C1, C1, with those components, negative C1, C1, you just get that by taking C1 and multiplying it by negative 1, 1. So that, you know, scalar multiplies each component. Similarly, the second part here, you just multiply C2 by 3/2 and 1, that vector with 3/2 and 1, and you'll get that vector. Are there any questions up to here? Hopefully it's pretty intuitive. Hopefully. Okay, one moment here. Okay, so if you're good then, here, of course, if the vector 1, 4 equals the sum of these two vectors, then this leads us to these two equations. And we can solve those two equations easily. I mean, you know, when you know how to solve systems of equations, right? It comes up in partial fractions all the time, right? So C2 will equal 2, C1 will also equal 2, and so then the solution to the IVP, what's IVP stand for, class? What does IVP stand for? Do you remember? Initial value problem. That's right, Hu Young. Very good. Very good. So this then is our solution to that initial value problem. All right, and please let me know if you have any questions. All right, well, so the vector x has two components. Okay? So, I mean, I think you can see that the first component would be t to the e to the negative 1t times negative 1 plus 2 times e to the 4t times 3 halves. That's the first component. The second component would be 2 times e to negative 1t times something plus 2 times e to the 4t hold on. That's a 4t times something. What numbers are going to go there? What would go here and here?
1.
Yep, that's right, Justin. And
1.
perfect. Okay. So we can then, you know, so the vector x, right? The vector x is a vector of x it's the vector that contains our xy functions. Okay, so this means then that x of t equals this function, and y of t equals this function. And I'll show that on the next page. Okay, so hopefully we're good here. We got it right here, x and y. And remember, x is a function of t, and y is a function of t. And we treat these like coordinates, right? Like coordinates. Just like the phase, and we can plot those coordinates on a phase portrait, just like you did in one of your MATLAB assignments. Or I guess there were two where you used a phase portrait, right? But you see, if this particle, the movement of the particle, if it's modeled by those differential equations where dx dt gives the velocity of the particle with respect to time in the x direction, and dy dt gives the velocity of the particle with respect to time in the y direction, then the coordinates of x and y as a function of time are given here. And I notice that these coordinates are going to increase with t as t goes to infinity, because you have the 4 to the t power. And this will actually trace out a solution on the phase portrait given in figure 8.2.2. And I'm actually going to display that for you as soon as you're done copying this. Are there any questions at all? So keep in mind, for our problem, initially at time 0, x of 0 was equal to 1. Let me see, right? And y of 0 was equal to 4. So in terms of like, if we think about an xy axis here, and we think about the coordinate, 1, 4, say that's 1, 4 there, 1, 4. Then with respect to time, this particle, hold on here, one moment. This particle has to fly off away from the origin. That would be the trajectory of the particle. And this is confirmed. Let me just go to the book real quick, because this is confirmed in figure 8.2.2. Well, they've drawn a lot of trajectories. The phase portrait of the system, so all those different trajectory curves correspond to different initial conditions. Remember, in MATLAB, you had different initial conditions and you got a lot of trajectory curves, right, for one of the MATLAB assignments. Well, so our trajectory curve that starts off at time equals 0 at 1, 4 would be in the first quadrant. But you can see that all the trajectories move away from the origin. And that's because the x and y coordinates get bigger and bigger and bigger. So they move away from the origin. And they actually also, there's theory regarding in the picture about eigenvectors and eigenvalues, but we won't get into that. I just wanted to, Math 284 linear algebra will be excellent for that. I think we've done a reasonably good job in one class of covering really key stuff. Are there any questions at all? Okay, let me stop the recording.